In 1998, in a quiet office in Cambridge, a young physicist pushed open a door and found complete silence. A man sat motionless in a wheelchair, smiling gently, while an old screensaver scrolled across his monitor, to boldly go where Star Trek fears to tread. The man was Stephen Hawking, and he had summoned his visitor to discuss one question, the one he would spend his last 20 years answering, eventually at 1 word per minute. Where does time actually come from? The textbook answer is the Big Bang. 13.8 billion years ago, the clock started ticking. But the equations that predict the Big Bang destroy themselves at the Big Bang. The afterglow of that first fireball still fills every room on Earth. 411 ancient photons in every cubic centimeter of air. Yet not one of them reaches back to the beginning itself. And when Hawking traced time all the way down, he found no first moment at all. No first tick, no wall. Something far stranger. By the end of tonight, you will know what the true origin of time is, and why it is not the Big Bang. Settle in, hit subscribe if you're new here, because by the end of this, the word always will never sound quite the same again. Now, let's slowly ease into this. Part 1. The Door. In Cambridge. The question of where time comes from was reopened, in our lifetime, by a man who could not speak. He answered it 1 letter at a time, at a pace slower than a heartbeat, and the answer he left behind is not the one the textbooks teach. Tonight we are going to follow that answer all the way down, beneath the Big Bang itself, to the place where clocks stop meaning anything at all. It begins with a door. It is 1998 in Cambridge, England, and a young Belgian physicist named Thomas Hertog is standing outside an office in the Department of Applied Mathematics and Theoretical Physics. He has been summoned here, though he does not entirely know why. He pushes the door open slowly, and the first thing that greets him is silence, complete silence. There is a man in a wheelchair in the middle of the room, motionless, smiling gently, watching him. On the computer monitor beside the chair, an old-fashioned screensaver is scrolling, the kind where a line of text drifts across a dark screen, over and over. The text reads, "To boldly go where Star Trek fears to tread." Nobody says anything, because the man in the chair cannot say anything, not in the ordinary way. Somewhere in the machinery attached to his wheelchair, a cursor is crawling across a grid of letters, and the man is selecting them, one at a time, with a small movement of his hand. The room hums quietly. The young visitor waits. It takes minutes for the first sentence to assemble itself. Then the machine speaks in a flat, American, synthetic voice, and the conversation begins. The man in the chair is Stephen Hawking, and this, Hertog will later learn, is Hawking's version of a job interview. The man conducting that interview had been given 2 years to live 35 years earlier. In 1963, during his first year as a doctoral student at Cambridge, Hawking was diagnosed with amyotrophic lateral sclerosis, a disease that progressively shuts down the nerves controlling voluntary movement. He was 21 years old, and the doctor's estimate gave him until roughly his 23rd birthday. He lived to be 76. Along the way, in 1985, a near-fatal bout of pneumonia and the tracheostomy that saved his life took away his natural voice entirely, which is why, by the time Hertog walks through that door, Hawking speaks through a computer. In the early years, he could select words at a rate of a few per minute. In his final years, steering the cursor with a single cheek muscle, read by an infrared sensor mounted on his glasses, the rate fell toward 1 word per minute. Hold that number for a moment, because it matters for everything that follows. 1 word per minute means that a single paragraph is an afternoon. It means that every idea in the theory we are going to explore tonight passed through the narrowest communication channel in the history of science, and came out the other side anyway. The question Hawking wanted to discuss at that first meeting was not a technical puzzle about black holes, although black holes were his home territory. It was one of the oldest questions humans have ever asked, dressed in the language of physics. Why is the universe the way it is? Why do the laws of nature seem so precisely arranged that stars can burn, that chemistry can happen, that something like you can exist and wonder about it? And buried inside that question, like a seed inside a seed, was a harder one. What is the true origin of time? Not what happened early in time. Where does time itself come from? That is the question this video is about. And I want to make you a promise at the outset. By the end of tonight, you will have the answer that Hawking spent his last 20 years building. It is not the answer he started with. It is not the answer most of us were taught. And it is going to take the whole night to earn it. Because the answer only makes sense once you have watched every other answer fail. Hertog had never met a physicist who asked questions like this. Hawking had famously declared, in print, that philosophy was dead, that it had failed to keep up with modern science. And yet here he was, in the privacy of his office, guided by the very questions philosophy was invented for. Where do we come from? What is our place in the grand scheme of things? In his heart, Hertog came to believe Hawking was a humanist, someone who cared about what the universe means for the people inside it. The physics was the instrument. The question was older than the instrument. One way or another, Hertog survived the interview. What followed was a doctoral thesis, and then a collaboration that ran for roughly 20 years, until Hawking's death on March 14, 2018. Their final joint paper was published in May of that year, weeks after he died. He worked on it, quite literally, until the end. The collaboration itself was unlike anything else in science, and its texture is part of the story. Hawking could not write equations. He could not hold chalk, could not sketch on paper, could not do any of the things theoretical physicists do all day, so he worked in pictures. He would ask Hertog to draw a diagram on the blackboard, and then steer it, word by patient word, with single syllables and the movements of his face. Circles and discs became his instruments. A whole afternoon might produce one refined drawing. In the later years, when even the cheek muscle grew unreliable, Hertog would position himself in front of Hawking and ask questions shaped for yes or no answers, reading the reply in his eyes, reconstructing arguments from fragments and from 2 decades of shared context. The theory they built was not dictated, it was triangulated, slowly, between one of the most ambitious subjects in physics and one of the most constrained conversations ever held. There is something worth sitting with in that image. The origin of time, worked out by a man for whom every minute was rationed. After Hawking's death, Hertog spent years completing the framework and presenting it to the world, and in 2023 he published a book that lays it all out. The book is called On the Origin of Time. If that title sounds familiar, it should. It is a deliberate variation on another famous title, On the Origin of Species, the book in which Charles Darwin explained where the living world comes from. For now, just file that away. The reason a book about cosmology is named after the founding text of biology is one of the strangest and most beautiful ideas we will meet tonight, and we are not ready for it yet. When it arrives, near the end of our journey, it will change what the word law means. Before we go further, I want to be clear about the stakes, because this is not a detail of cosmology, some decimal point argued over at conferences. The question of where time comes from decides whether some of the most basic words you use every day actually mean anything. Before, after, always, beginning. Every plan you have ever made, every memory you carry, every sentence you have ever spoken relies on the assumption that time simply is, a stage on which everything else performs. If time turns out to be something that was made, something that has an origin the way a river has a source, then the stage itself is part of the play, and the script has to be rewritten from the first line. That is what Hawking came to believe, not as a metaphor, as physics. To understand how he got there, we cannot start with time at all. We have to start with something that looks, at first, like a completely different subject. The question Hawking posed in that silent office, why the universe is fit for life, turns out to be welded to the question of time so tightly that answering one answers the other. And to see the weld, we first have to meet the thing being questioned, not the universe, the laws that run it. Because the strangest discovery of the last 4 centuries is not any particular law of nature. It is the fact that there are laws at all, written in mathematics, obeyed everywhere, by everything, without exception. Where do the laws themselves stand, while everything else obeys? That is where our story truly begins. Part 2. The Cosmic Barcode. The idea that nature obeys laws is so familiar that we forget someone had to think of it. As far as we can tell, the first person to say it out loud lived about 26 centuries ago in the Greek city of Miletus. His name was Anaximander, and his proposal was simple and radical. Not only human societies are governed by rules, he said, but nature is too. The seasons, the seas, the stars, all of it answering to some kind of order, whether or not anyone is watching. It took 2,000 years for that intuition to become an instrument. In 1687, Isaac Newton published the Principia, and for the first time, the laws of nature were written down in the language of mathematics. The same equations that described a falling apple described the orbit of the moon. One set of rules, from the ground beneath your feet to the edge of the visible sky. Something subtle happened next, and it shaped the next 300 years of thought. The laws worked so well that they began to take on a life of their own. Newton himself promoted them to something close to transcendental truths, rules that stand outside the universe, prior to it, the way a legal code exists before any particular case is tried. On this view, the universe does not merely have laws. The universe answers to laws, the way a defendant answers to a court that was already in session before he walked in. Physicists came to picture the laws as a kind of cosmic barcode, a birth certificate, issued to the universe at the moment of delivery, specifying exactly what it would be: these forces, these particles, these constants, this fate. The barcode was printed first, the universe followed. The high watermark of that confidence has a date and a name. By the 1840s, astronomers had noticed that the planet Uranus was misbehaving, drifting slightly off the path Newton's equations prescribed. A French mathematician named Urbain Le Verrier sat down with the discrepancy and did something audacious. He assumed the law was perfect and the map was incomplete. If Newton's equations were right, then something unseen was tugging on Uranus, and the equations could tell him where it was. He calculated the position of a planet nobody had ever seen. On September 23, 1846, the astronomer Johann Galle, in Berlin, pointed his telescope at the predicted spot and found Neptune within 1 degree of where Le Verrier's arithmetic said it would be, on the first night of searching. Think about what that meant to the people who lived through it. A man had discovered a world without looking through a telescope, using nothing but ink and the conviction that the rules of reality were written down somewhere and could be read. If you want to know why generations of physicists believed the laws of nature were eternal and untouchable, that night in Berlin is why. Now jump forward to our own decade, because the same laws have been putting on a show for us. On Christmas Day, 2021, a rocket lifted off from the coast of South America, carrying the James Webb Space Telescope, folded up like a piece of origami, because no rocket is wide enough to carry it open. Over the following weeks, it unfolded itself in space, spread a sun shield the size of a tennis court, assembled a segmented mirror 6.5 meters across, and settled into position around a point in space about 1.5 million kilometers from Earth. roughly 4 times farther away than the moon. From that dark, cold vantage point, it began to photograph the universe, and among its first showcase images was a scene astronomers nicknamed the Cosmic Cliffs, towering rims of gas and dust on the edge of a star-forming region in the Carina Nebula, about 7,600 light-years from here. Places like that are where stars and planets are born. And inside those clouds, telescopes find not just hydrogen and helium, but organic molecules, carbon-bearing compounds, the basic ingredients that chemistry will one day assemble into the building blocks of living things. Sit with that for a second. The raw materials of life are not rare or exotic. They are drifting in the nurseries where stars are made. Everywhere we look, the universe is not merely compatible with life. It is stocked for it. That word, stocked, is where the comfortable story starts to itch. Because when you ask why the universe is so hospitable, the answers keep tracing back to those laws, and to numbers inside them that nobody has ever explained. Consider dark matter. The universe contains roughly 5 times more of it than ordinary matter, an invisible gravitational scaffolding, and without it, the early universe's faint clumps of gas would have been too feeble to pull themselves together into galaxies before expansion spread them thin. No dark matter, no galaxies, no stars. Consider something even more basic. So basic you have never thought to question it. Space has 3 dimensions. In 1917, the physicist Paul Ehrenfest proved that this is not a decoration but a requirement. In a universe with 4 or more dimensions of space, planetary orbits are unstable, and so are atoms. Electrons would spiral into their nuclei or fly away entirely. In fewer than 3, the connections that make complex structures possible become geometrically strangled. 3 is not just what we have, 3 is what works. The list keeps going, and it gets more uncomfortable as it goes. In 1953, the astronomer Fred Hoyle reasoned that carbon, the backbone element of every living thing on Earth, could only be manufactured inside stars in meaningful quantities if the carbon-12 nucleus happened to have a special excited energy state at a very particular level, about 7.65 million electron volts above its ground state. No one had ever measured such a state. Hoyle essentially predicted it from the fact of his own existence. We are made of carbon, therefore the state must be there. Experimenters at Caltech went looking and found it, within months, almost exactly where he said it would be. Hoyle, a lifelong atheist, later admitted that nothing had shaken him like that result. The universe, he said, looked like a put-up job, and looming over all of these is the strangest number in physics. Empty space, it turns out, is not nothing. It carries an energy, called the cosmological constant, which pushes the universe's expansion to accelerate. When physicists try to calculate its value from quantum theory, the naive answer comes out too large by a factor of up to 10 to the power of 120. That is a 1, followed by 120 zeros. The measured value is absurdly, precisely small, and it has to be. A universe with a substantially larger value would have blown itself apart before a single galaxy could form. A large negative value, and the universe recollapses in a hurry. Back in 1987, the physicist Steven Weinberg pointed out that the constant could not be much bigger than what we now observe, or nobody would be here to measure it, an argument that turned out numerically prophetic and philosophically radioactive. And the margins show up everywhere you press. The neutron is heavier than the proton by about 0.14%. And if that tiny imbalance ran the other way, hydrogen itself would be unstable. And stars, as we know them, could not exist. Nudge the strong nuclear force a few percent weaker, and stars lose their fuel chain. A few percent stronger, and the infant universe burns through its hydrogen. The astronomer Martin Rees has argued that just 6 numbers, none of them derived from anything deeper, hold the whole habitable arrangement in place. Every one of these facts passes through the same needle's eye, and the needle's eye is the barcode. The old answer to this pattern was design. Aristotle spoke of final causes, of nature aiming at ends, and for most of history, the hospitable universe was read as evidence of intention. Modern science set the designer aside and put the eternal laws in his chair. But notice what that exchange actually accomplished. The mystery did not shrink. It moved. Why these laws? Why this barcode, and not another, out of the endless barcodes that would have printed a sterile universe? Nothing in the laws explains the choosing of the laws, and it is worth being honest about what hangs on the question, because this is not abstract. The iron in your blood was forged inside stars that only exist because these particular numbers hold. You are, atom by atom, a consequence of the arrangement nobody can explain. This was the question sitting in the silence of that Cambridge office. Why is the universe fit for life? All the way down to the mathematics. But here is what you could not yet know, and what Hertog could not know, as he stood in that doorway. To answer it, physics would have to find out where the barcode itself came from, and that search leads, step by inevitable step, backward, to the beginning, to the origin of time. And the story of how humanity even discovered that time might have an origin does not start with Hawking at all. It starts 70 years earlier, with a quiet man in a Roman collar, bent over a sheet of graph paper, about to run the history of the universe in reverse. Part 3. The priest who ran the film backward. The equation at the center of this story was written in 1915, and it is, by common agreement among physicists, one of the most beautiful objects human beings have ever made. Einstein's field equation of general relativity is a dialogue conducted across an equals sign. On the left side sits geometry, the shape of space and time, how they curve and stretch. On the right side sits matter, everything that has mass and energy. And the equals sign in the middle is where the magic happens, because it declares that the two sides are locked together. Matter tells space and time how to curve. Curved space and time tell matter how to move. In 1917, Einstein added one more term to the equation, a small Greek letter lambda, an energy belonging to space itself, because without it, his universe refused to stand still, and he was certain as everyone else in 17 centuries of astronomy, that the universe stands still. Remember that lambda. It will come back tonight wearing different clothes. The trouble began with a Belgian. Georges Lemaitre was a genuine oddity in the physics of his era, an ordained Catholic priest who was also a mathematically formidable cosmologist, a man who wore a Roman collar to scientific conferences. In 1927, working through Einstein's equations, he made the discovery that would define the century. If you apply the equation not to a planet or a star, but to the entire universe at once, it refuses to describe a static cosmos. Space itself, the equations insisted, should be expanding. And Lemaitre went further. From the sparse astronomical data available, he derived the rate at which galaxies should appear to recede from us, deriving a version of the law of cosmic expansion 2 years before Edwin Hubble published the observations that made it famous. A Russian mathematician named Alexander Friedman had found the expanding solutions even earlier, in 1922. But it was Lemaitre who welded the mathematics to the sky. When Lemaitre explained his result to Einstein at a conference in Brussels, Einstein's reply has become legend. "Your calculations are correct," he said, "but your physics is abominable. It helps to be precise about what expanding space means, because the phrase is easy to mispicture. The galaxies are not flying apart through space, like shrapnel from an explosion in a room. Space itself is stretching, and the galaxies are carried along with it, the way raisins in a rising loaf of bread move apart, not because they are swimming through the dough, but because the dough between them is growing. Each raisin, from its own point of view, sits still, and watches every other raisin recede. And the farther away a raisin is, the faster it appears to retreat, because there is more rising dough between them. This is why the expansion has no center. Every galaxy sees the same thing. Every point is the middle of the loaf. And then came the act of genius, the single move on which everything tonight depends. Lemaitre said, "If that is the picture, then let us turn the arrow around. Let us run the history of the universe backward. If space expands toward the future, then tracing it into the past means compression, everything drawing together, the loaf shrinking. Follow the film in reverse far enough, and the compression has no limit. Space and time curve more and more violently, until, at a finite moment in the past, the fabric of space and time destroys itself. Density becomes infinite. Curvature becomes infinite. And here is the detail that made this bad news for Einstein personally. At that moment, his own equation dies. The masterpiece with the equals sign stops computing. The theory predicts a beginning, and then fails at its own prediction, like a court that sentences itself. That moment of self-destruction is what the world would later learn to call the Big Bang. Picture him now, because this is a scene worth entering. It is late in 1929, or early 1930, in Leuven, Belgium. A man in a priest's collar sits at a desk with a fountain pen and a sheet of millimeter paper, the finely gridded graph paper that scientists used for precision drawing in the age before computers. He is plotting universes. Each curve he draws by hand is an entire possible cosmos. Along the horizontal axis runs time. Along the vertical axis, the size of the universe. He draws one that rises and crashes back down. He draws another that flees upward forever, thinning into emptiness. Curve after curve, a zoo of possible worlds, each one a complete history from birth to fate, rendered in ink strokes a few centimeters long. And in the corner of the page, in his careful handwriting, he marks the starting point of them all. T equals 0. The first instant. As far as we know, this is the first time in any scientific document that a human being wrote down the beginning of time as a physical event, something you could put on a graph. And as his pen moves across the grid, this quiet man is, at this moment, the only person alive who is conscious of living inside an expanding universe. Everyone else on Earth, every astronomer, every philosopher, every child looking up at the night sky, still inhabits an eternal, motionless cosmos. He knows something the entire species does not. When Lemaitre later published his systematic exploration of these solutions, in 1933, the zoo turned out to have a disturbing feature. Nearly every universe in it is sterile. The ones that expand and recollapse quickly are over before stars can form, a flash and then nothing. The ones that expand too fast spread their matter so thin that gravity can never gather it into galaxies. Among all his hand-drawn worlds, Lemaitre found one, a single delicate curve that lingers, a universe that expands, then hesitates, almost pausing for billions of years, giving gravity the time it needs to condense gas into galaxies and stars before expansion resumes. He called it the hesitating universe, and he could see in his own ink that it was the only curve on the page with room in it for cliffs of gas in Carina, for carbon, for readers and listeners. The question that would sit in Hawking's silent office 65 years later, why this universe and not another, is already there, drawn by hand, on a piece of Belgian graph paper. Now consider the position this man was in, because it is one of the loneliest in the history of thought. He has discovered, or believes he has discovered, the beginning of the world. He is a priest, and he knows exactly what everyone will assume, that the collar wrote the conclusion, that he has smuggled Genesis into the equations. He is a scientist, and he knows the physics community regards a cosmic beginning as scandal, as bad taste, as religion wearing a false moustache. He cannot shout it from a pulpit, and he cannot shout it at a conference. So he folds what he has found into a poem. He writes of the first instant as the now, which has no yesterday, because yesterday there was no space, and there was no time for a yesterday to live in. Hold on to that phrase tonight. The now which has no yesterday. It sounds like mysticism. It will turn out, before we are done, to be a strangely precise description of what the physics actually says. And notice what the poem quietly insists on. The Big Bang, for Lemaitre, was never just an explosion at the start of history. It was the origin of history's container, not an event in time, the arrival of time. He gave the idea a scientific name as well as a poetic one. In a short note published in the journal Nature on May 9, 1931, barely a page long, Lemaitre proposed that the universe began as what he called a primeval atom, a single, undifferentiated quantum of existence, containing everything that would ever be, which then fragmented and expanded into the world. And he added a sentence that physicists would spend the next century catching up to. The beginning of the world, he wrote, happened a little before the beginning of space and time. Read that again. Not at the beginning of time, before it, in some sense that ordinary language strains to hold, an abstract state out of which space and time themselves would emerge. Nobody in 1931 had the tools to make that sentence precise. Keep it in mind, because the man in the wheelchair in Cambridge will spend his final 20 years building exactly those tools. Years later, when the idea had escaped the graph paper and grown famous, it acquired admirers Lemaitre had not asked for. In 1951, Pope Pius XII declared in a public address that the primeval beginning, discovered by modern cosmology, amounted to scientific support for the doctrine of creation. You might expect the priest who founded the field to be pleased. He was horrified. Lemaitre insisted, publicly and privately, that his cosmology proved nothing about God, that the equations were silent on such matters, and he worked behind the scenes, through the Vatican's own Academy of Sciences, to make sure the argument was not repeated. The beginning he had found was physics, he maintained, and it had to stand or fall as physics. It is one of history's finer ironies, the man in the collar, defending the Big Bang from religion. But an idea this size cannot live in one man's notebooks and one poem. It needed the world to hear it, and the world very nearly did not. The story of how it broke out is a story of a meeting Lemaitre missed, a forgotten article in the wrong language, and a chain of letters passed between astronomers like a rumor. And it ends with a sound, a faint, patient hiss, falling out of the sky onto New Jersey. Part 4. The Letter and the Hiss. On January 10, 1931, the Royal Astronomical Society convened in London for one of the most consequential meetings in the history of the field, and the man whose idea was on trial was not in the room. By then, astronomers had accepted the observational fact: the galaxies are moving away from each other, and the farther they are, the faster they flee. What nobody in that room could supply was the explanation. The assembled scientists, including Arthur Eddington, the most influential astronomer in Britain, discussed the puzzle and went home without an answer. Lemaitre was in Belgium. He read about the meeting afterward, in the printed proceedings, and one imagines the particular flavour of that moment. The world's experts, publicly stumped by a question he had answered 4 years earlier, in a paper published in French, in a minor Belgian journal, that nobody had read. So he wrote a letter. He wrote to Eddington, who had actually been his teacher years before in Cambridge. And the substance was simple. I believe I have solved the problem you discussed. The galaxies recede because space itself is expanding. Eddington, to his lasting credit, recognized what he was holding. He wrote to his colleague Willem de Sitter in the Netherlands. De Sitter wrote back, and wrote to Lemaitre. And finally Lemaitre wrote to the Royal Astronomical Society with a practical offer. He would translate his 1927 article into English so the community could read it. That chain of letters, passed from hand to hand across 3 countries, like a rumor slowly being confirmed, is how the expanding universe entered world science. The translation appeared in the Society's monthly notices in 1931, and with it, the idea was loose. The translation carries a small mystery of its own, one that took 80 years to solve. Readers eventually noticed that the English version was missing something. The paragraph in which Lemaitre had derived the rate of cosmic expansion from data 2 years ahead of Edwin Hubble, whose name ended up on the law. For decades, suspicion simmered that someone, perhaps partisans of Hubble's priority, had censored the translation. When the correspondence finally surfaced, the culprit turned out to be Lemaitre himself. Translating his own paper, he had simply cut the paragraph, reasoning that the data it relied on was 4 years old and had been superseded by better measurements. He was not interested in credit. He was interested in being current. In 2018, the International Astronomical Union voted to write the ledger, formally renaming the law of cosmic expansion the Hubble-Lemaitre law, 91 years after the quiet priest first wrote it down. But acceptance of the expansion was not acceptance of the beginning. Through the 1930s, 40s and 50s, most physicists drew a hard line. Fine, space is stretching, but driving the film all the way back to a moment when the entire universe was a fireball of billions of degrees, that was regarded as extravagance. One prominent assessment dismissed it as speculation run mad. The resistance even named the theory by accident. In March of 1949, on BBC Radio in London, the astronomer Fred Hoyle, the same Hoyle who would later predict the carbon resonance and who championed a rival picture in which the universe had existed forever in a steady state, reached for a dismissive image for this idea that everything began in one hot instant and called it a Big Bang. The name was meant to sting. It stuck instead, and it stuck to the most successful theory in the history of cosmology. What settled the argument was not a debate, it was a noise. In 1964, 2 radio astronomers at Bell Laboratories in Holmdel, New Jersey, Arno Penzias and Robert Wilson, were commissioning a large horn-shaped antenna, and they had a nuisance on their hands. A faint, persistent microwave hiss that would not go away. They pointed the horn at different parts of the sky. The hiss was there. They pointed it away from the galaxy. Still there. They checked the wiring, considered interference from New York City, and at one point evicted a pair of pigeons nesting in the horn and scrubbed away what the official account delicately called a white dielectric substance. The hiss remained, identical in every direction, day and night, season after season. It was not coming from the antenna, or the city, or the galaxy. It was coming from everywhere. What they had found, it soon became clear, was the afterglow of the hot Big Bang itself. Light released when the universe was young, stretched by 13.8 billion years of cosmic expansion, until it arrives today, as microwaves, at a temperature of 2.7 degrees above absolute zero. The steady-state universe had no way to produce such a glow. The fireball did. The argument was over, and in 1978, the 2 men who had chased pigeons out of their antenna received the Nobel Prize in Physics. The numbers behind that glow deserve a moment, because they are the vital statistics of our origin. The light was released about 380,000 years after the beginning, the moment the universe cooled to roughly 3,000 degrees and became transparent for the first time. Before that, it was a glowing fog, too dense for light to cross. Expansion since then has stretched every wavelength by a factor of about 1100, which is why a glow that began at the temperature of a star's surface now whispers in at 2.7 degrees. And it is not somewhere out there. It is here, in the room with you. Roughly 411 of these ancient photons occupy every cubic centimeter of space, including the space inside your body. On an old analog television, tuned between stations, about 1% of the dancing static on the screen was this light, the Big Bang, playing on every set on Earth. Then the afterglow turned out to contain a message. Satellite missions, beginning with COBE in 1992 and refined by WMAP and then Planck, mapped the glow's temperature across the entire sky and found that it is not perfectly uniform. It varies, from patch to patch, by about 1 part in 100,000. The Big Bang, in other words, flickered. And those flickers are the most important imperfections in existence, because in the slightly denser, slightly hotter patches, gravity had a head start. Dark matter gathered there first, gas fell in after it, and over hundreds of millions of years, those 1 in 100,000 differences grew into the first stars, then galaxies, then clusters of galaxies, then, eventually, at least one rocky planet where the glow could be measured. Had the early universe been perfectly smooth, gravity would have had nothing to grip, and nothing would ever have formed. No stars, no carbon, no listener drifting towards sleep. You are descended from the flicker. The Planck satellite's final analysis, published in 2018, read the universe's age out of that map, 13.8 billion years, with an uncertainty of only a few tens of millions, a margin of about 1 part in 1,000, on the oldest date there is. Lemaitre lived just long enough to hear the news. He was in his final years when word reached him that a glow had been found falling out of the sky, exactly the kind of fossil light his fireball beginning demanded, and he died in 1966, knowing the idea he had carried alone, through decades of polite dismissal, had hardened into measured fact. 2 years before his death, in 1964, Belgian television recorded a long interview with him, the only substantial footage of the man explaining his own ideas. Then the tape was lost. It sat misfiled in the archives of the Belgian public broadcaster for roughly 50 years before resurfacing in the 2020s, so that our century got to watch, as if through a reopened door, the founder of the Big Bang describe in his own voice a beginning that was not an explosion in space, but the arrival of space and time themselves. And there the story could end, triumphant. The beginning was real. It flickered, it glowed, it dated itself. But you may have noticed that everything we have confirmed lies after the beginning. The glow is a photograph taken 380,000 years in. The flicker is structure already seeded. The one thing none of it touches is the first instant itself, the t equals 0 in the corner of Lemaitre's graph paper. And when physicists finally pushed their equations toward that instant, they found something waiting that was far worse than a gap in the data. They found that the theory that had predicted the beginning could not survive its own prediction. Part 5. The Achilles heel. Let us take stock of where we stand, because the 2 threads of our story are about to weave together. In a silent office in Cambridge, a question is waiting. Why is the universe fit for life? And where does time come from? And out in the world, a theory has triumphed. The universe began 13.8 billion years ago in a hot, flickering fireball whose afterglow still fills every room on Earth. Here is the uncomfortable truth those 2 threads share. The Big Bang is at once the cornerstone of modern cosmology and its open wound. The entire 13 billion year picture hangs together beautifully, from the first flicker to the cosmic cliffs, and all of it hangs from a first instant that the theory itself cannot describe. Watch what happens when you push Einstein's equation all the way home. Run the expansion backward, as Lemaitre taught us, and the universe compresses. The temperature climbs, the curvature of space and time sharpens. So far, so good. The equations handle the fireball with grace, but the compression does not level off. As you close in on time 0, the density heads toward infinity. The curvature heads toward infinity, and an equation fed infinity stops being an equation. It becomes a row of symbols that no longer computes anything. At the moment the theory identifies as the beginning, the beautiful dialogue across the equals sign, matter on one side, geometry on the other, collapses into noise on both sides at once. Physicists call this a singularity, which is a technical way of saying, here, the theory files for bankruptcy. General relativity predicts a first moment, and then, at that very moment, self-destructs, a court that reads out a sentence and dissolves before it can be enforced. For a while, there was a respectable hope that the singularity was a bookkeeping artifact. Perhaps it appeared only because cosmologists assumed the universe was perfectly smooth and symmetric. Perhaps a lumpier, more realistic universe would sidestep the infinity, its ingredients slipping past each other in reverse rather than piling into one point. That hope was executed with mathematical precision in the late 1960s. Roger Penrose, and then a young doctoral student named Stephen Hawking, proved a series of results now known as the singularity theorems, which showed that under broad, realistic conditions, no such escape exists. The breakdown is not a special feature of tidy models. It is generic. Almost any universe governed by general relativity and filled with ordinary gravitating matter must trace back to a point where the theory fails. Penrose would eventually share the Nobel Prize, in 2020, for work in this line, and savour the irony, because it is one of the finest in physics. Stephen Hawking's early reputation was built on proving that the beginning of time was unavoidable. The man in the wheelchair spent his youth barricading every exit from the singularity, and his final 20 years quietly dismantling the assumption that made it a wall. The dates are worth fixing in your mind, because they frame Hawking's whole life in physics. Penrose published the first of these theorems in 1965, originally about the collapse of stars into black holes. Hawking, hunting for a thesis topic and newly aware that his own time was rationed, realized the same logic could be run in reverse on the entire universe, and by 1970, the two of them had together proved the general result. A beginning was not optional. It was forced. The young man who had been told he would not live to finish his doctorate had made the beginning of time mathematically inescapable, and the result made his name. Which is precisely why his final theory carries the weight it does. This is not a case of an outsider taking a swing at the Big Bang. The man who closed every loophole is the one who came back, half a century later, to say the wall itself had been misread. Now stand at that wall and try to ask the obvious question, what came before? Notice that the question dissolves in your hands. If time itself begins at the singularity, then before is a word without a referent, like asking what is north of the North Pole while standing on it. There is no earlier moment for a cause to live in, but be careful, because the standard reply, time simply starts there, and the question is meaningless, is not an answer either. It is a no trespassing sign. Saying that time begins, full stop, explains the beginning of time, exactly as well as saying that the barcode was printed, explains who printed it. When there was no when for a printer to operate in. The laws of nature, our supposedly eternal court, turn out to have no jurisdiction over their own first act. Either something deeper than general relativity takes over at the beginning, or physics ends one step short of its own front door, and the beginning hides a second scandal, quieter, and, to many physicists, even more troubling. Look closely at the laws of nature, and you find that they are almost perfectly symmetric in time. Run nearly any fundamental process in reverse, and you get another process the laws permit. Yet nothing in your experience is symmetric in time. Eggs break and never unbreak. You remember breakfast and not tomorrow. This one-way flow, the arrow of time, is not written in the fundamental laws. It is inherited, through the logic of thermodynamics, from the initial condition, from the simple, stunning fact that the universe began in a state of almost inconceivable order and has been unwinding ever since. How inconceivable? Roger Penrose estimated the odds of so ordered a start, under conventional assumptions, at 1 part in 10 to the power of 10 to the 123, a number so large that writing out its zeros would require more digits than there are particles in the observable universe. Every clock that ticks, every star that burns, every memory you form is spending order that was banked in the first instant, and nobody can say why the account was full. Any honest theory of time's origin owes us not just a beginning, but a loaded beginning, wound up and pointed. There is also a hard limit on what looking can do for us here, and it is worth being clear about it. The oldest light in the universe is the afterglow, released 380,000 years in. Earlier than that, the cosmos was an opaque fog, and no telescope, however large, will ever photograph past it. The first fraction of a second, where the origin of time lives, is hidden behind that wall of fog, and then hidden again behind the failure of the equations. Only one kind of messenger could ever carry news out of that era: gravitational waves, ripples in space and time itself, which pass through fog, plasma, and everything else as if they were not there. File that thought away. Near the end of tonight, it becomes the entire hope of testing what we are about to build. The scale of the required repair is set by two tiny numbers. Follow the compression down to about 10 to the minus 44 seconds, an interval so brief that there are more of them in 1 second than there are seconds in the age of the universe many times over, and to distances around 10 to the minus 35 meters. And you reach the regime physicists call the Planck scale, where the smooth geometry of general relativity must give way to something quantum. At that frontier, the two great theories of the 20th century, general relativity, which owns the large, and quantum mechanics, which owns the small, are both required and mutually incompatible, a marriage that has been announced for a century and never performed. The beginning of the universe is the one event where neither theory can politely defer to the other. Whatever describes it must be both at once. So let us restack the pieces, slowly, because they now form a very strange pile. The universe is governed by mathematical laws so precise that a man once found a planet with ink. Those laws contain unexplained numbers tuned to absurd margins in favor of stars, carbon, and you. The universe these laws govern began, measurably, 13.8 billion years ago, in a state of order so extreme it beggars arithmetic. And at the beginning itself, the laws fail, taking with them the very words before and cause. A barcode with no printer, a beginning with no description, a question waiting in a silent office in Cambridge. By the late 1990s, the physicists who thought hardest about this had grown frustrated enough to try something desperate. If one beginning is inexplicable, perhaps the answer is to abolish its loneliness. Perhaps our Big Bang was not the beginning, but a beginning, one of endlessly many, budding off forever inside something incomparably larger. It was called the multiverse, and for a time it looked like salvation. It would turn out to be the failure that forced the breakthrough, and it is where we go next. Part 6. The Detour Through Infinity. To understand the desperate move cosmology made in the 1990s, you first need one more piece of the standard story. In the early 1980s, physicists, led by Alan Guth and André Linde, proposed that in its first instance, around 10 to the minus 32 seconds, the universe went through a burst of expansion so violent it defies every analogy. A stretch by a factor of at least 10 to the 26, doubling and redoubling dozens of times in a sliver of a second, driven by the energy of a high-energy field filling all of space. They called it inflation, and it earned its keep by explaining things the plain Big Bang could not. Why the universe looks so uniform from one horizon to the other. Inflation took a tiny, well-mixed patch, and blew it up to cosmic size. Why space is so geometrically flat? Stretch any curved surface enough, and every neighborhood looks flat, as the surface of the Earth does to someone standing on it. Even the sacred flicker, the 1 part in 100,000, fell out naturally. Microscopic quantum jitters in the inflating field, enlarged to astronomical scale, and frozen into the sky. Inflation became, and remains, the working front end of modern cosmology. But inflation came with a stowaway. When Linde and Alexander Vilenkin worked through the mathematics, they found that in generic models, inflation does not know how to stop everywhere. It ends in some regions, which cool off and become ordinary universes like ours, while elsewhere, the inflating state keeps going, and because it inflates, the still inflating regions grow faster than they decay. The process feeds itself forever, endlessly budding off pocket universes, the way a boiling pot throws bubbles, except the pot never runs dry. This is eternal inflation. Our Big Bang, in this picture, was not the beginning of everything. It was a local event, one bubble bursting in an infinite, self-perpetuating foam. Then, string theory poured fuel on the fire. Around 2003, theorists surveying string theory's mathematical terrain concluded that it does not describe one possible universe, but an almost incomprehensible menu of them. A landscape of something like 10 to the 500 distinct configurations, each corresponding to a different set of effective physical laws, different particles, different forces, different constants. 10 to the 500 is not a number in any human sense. It dwarfs the count of atoms in the observable universe, which is a mere 10 to the 80, so thoroughly that comparing them is a category error. Marry the landscape to eternal inflation, and you get the full multiverse, an endless foam of bubbles, each bubble frozen into a different entry from the menu, every possible barcode printed somewhere, and every one of them printed infinitely often. It is worth pausing on what different laws would actually mean, because the phrase slides by too easily. In one bubble, the electron might be heavier, and atoms accordingly smaller, and chemistry rearranged or impossible. In another, there is no electromagnetism at all, and matter never learns to hold a shape. In another, space has 4 dimensions, and orbits cannot close, or 2 dimensions, and nothing complex can wire itself together. Some bubbles recollapse in microseconds, some expand so ferociously that no 2 particles ever meet again. The overwhelming majority are not merely lifeless but structureless, eternities of thin radiation or instant collapse, with nothing in between ever happening at all. And notice what that does to the question that has been haunting us since the cosmic cliffs. Why is our universe fine-tuned for life? In the multiverse, the answer is a shrug. All the settings are tried. Almost all the bubbles are sterile, their carbon resonance out of reach, their cosmological constant lethal, their dimensions wrong. But with infinitely many draws, the habitable arrangements come up too, and observers can only ever find themselves in those. Our barcode looks chosen because we are, by definition, in one of the winning tickets. The fine-tuning problem does not get solved so much as diluted to homeopathic strength in an infinite sea. Carl Sagan once distilled modern cosmic humility into a famous line: "We are chemicals on a medium-sized planet, orbiting an average star in an ordinary galaxy." The cosmologists of the 1990s appended a new clause: "In one of many universes, the final demotion. Even our universe is nothing special." Some physicists found this picture liberating, even beautiful. Hawking was not among them, and it is worth being precise about why. Because his objection was not a matter of taste. The cheap objection is obvious. You cannot visit another bubble, and no signal can ever cross between them. So the multiverse smells like metaphysics. But Hawking saw past the cheap objection to a fatal one. The problem is not that the multiverse is hard to test in practice. The problem is that it is untestable in principle, because it destroys the machinery of prediction itself. Here is the trap, and I will walk through it slowly. In an infinite multiverse, everything that can happen does happen, and happens infinitely many times. So when you ask, what should an observer expect to see? The honest answer requires counting. Of all the observers everywhere in the infinite foam, what fraction see this, rather than that? And infinity breaks counting. Compare the infinity of even numbers to the infinity of all numbers, and you can make the ratio come out as 1/2, or 1, or anything you like, depending purely on how you order the list. Cosmologists call this the measure problem, and it is not a technicality. Every proposed counting rule gives different predictions, and nothing in the physics selects the rule. A theory that predicts everything, with adjustable proportions, predicts nothing. It does not run the risk of being wrong. It loses the ability to be wrong, which is worse. Hawking put the discomfort more personally. The multiverse, he felt, describes the cosmos the way a surveyor describes a landscape he will never stand in, from nowhere, from outside, indifferent to the fact that every actual measurement ever made has been made from inside one particular universe by one particular observer. Something about the entire framing, he began to suspect, was wrong at the root. Wrong in a way that predated inflation and string theory, wrong in a way that went all the way back to Newton. It took years for that suspicion to become an argument. In fact, the very last paper he and Hertog finished together, published in May 2018, weeks after his death, was aimed at exactly this target. Using tools we will meet later tonight, they argued that eternal inflation's runaway infinity is not a discovery about reality, but an artifact, the result of stretching classical notions of space and time, a smooth background, a universal clock, into a regime where they simply do not apply. Treat the early universe with the right quantum tools, they claimed, and the infinite foam calms down. The ensemble of possible universes comes out finite, bounded, manageable. The multiverse, in their reading, was never a prediction of the physics. It was a symptom of the perspective. So pause here, at the low point of our story, and feel the shape of the impasse, because every road has now been tried, and every road has failed. The first grand answer said, there is one universe, dictated by one eternal, unique mathematical law, and someday we will read the law and understand why everything, including us, had to be this way. That was Einstein's faith, and decades of unification chased it, only to find not one forced answer, but a landscape of 10 to the 500 possibilities, with no principle to choose among them. The second grand answer said, fine, then all the possibilities are real, and we are an accident in the one corner that permits accidents like us. That was the multiverse, and it dissolved on contact with the simple question, what do you predict? One universe with an unexplained law, infinite universes with no predictions. A beginning that is confirmed by the afterglow in every cubic centimeter of this room, and indescribable by every equation we own. And here, precisely here, is where the story stops being about equations and becomes about a chair, a screensaver, and a sentence assembled one word at a time. Because in the early 2000s, in that office in Cambridge, Stephen Hawking became convinced that the entire argument, Einstein's side and the multiverse side alike, shared a single hidden assumption, one so old and so comfortable that nobody thought of it as an assumption at all. Both sides were describing the universe from a vantage point that does not exist, and the way out was not a new equation, it was a new place to stand. Part 7. The Wrong Perspective. One afternoon, sometime around 2002, in the office with the scrolling screensaver, the synthesizer spoke a sentence that Hertog says arrived somewhat out of the blue. Hawking had been sitting with the wreckage we surveyed in the last chapter, the unique law dream that fractured into a landscape, the multiverse that could not predict and the sentence he assembled, click by click, was not a formula. It was a diagnosis. Cosmology, he declared, had been done from the wrong perspective. There was no mathematics behind the claim yet, no derivation, nothing you could publish. It was one of those leaps of intuition Hawking enjoyed making, and this one would take the better part of 2 decades to cash out. But to understand what he meant, we have to go back 500 years and watch physics acquire the habit he was about to break. The habit begins with Copernicus, when he put the sun at the center of the solar system and set the Earth moving around it. Copernicus did something subtler than rearrange the furniture. He imagined stepping outside. To draw the solar system as circles around a central fire, you must picture it as seen from beyond it, from a vantage point no human has ever occupied, hovering above the plane of the planets, looking down. That imaginative step, out of your own body, off your own planet, to a viewpoint outside the system you are describing, turned out to be the most productive trick in the history of thought. Physicists sometimes call it the view from nowhere, or the God's eye view, and after Copernicus, it became the unspoken posture of all physics. Newton wrote his laws from that vantage, equations that describe the world as an object seen from beyond it, the same for all observers because they belong to no observer. The whole idea of the cosmic barcode, of laws standing outside the universe dictating its behavior, is this posture frozen into metaphysics. And let it be said plainly, the trick worked. It found Neptune with ink. It powered 3 centuries of discovery, and there is no reason to apologize for a single one of them. But every trick has a domain, and Hawking's diagnosis was that cosmology had quietly wandered out of this one's. Here is the assumption, hiding in plain sight, an observer outside the system. When the system is the solar system, that vantage point is a harmless fiction. You cannot stand there, but standing there breaks nothing, because the solar system does not care whether it is watched. When the system is the entire universe, the vantage point is not a fiction, it is a contradiction. There is no outside to stand in. There is no beyond from which the whole might be surveyed. Every observation ever made, every photograph of the cosmic cliffs, every measurement of the afterglow, every reading of every dial, has been made from inside, by observers who are themselves made of the system they are measuring, embedded in its history, downstream of its beginning. For most questions, this does not matter. A galaxy's rotation looks the same from inside the universe as it would from the imaginary outside. But for the questions we have been asking all night, why these laws? Why this beginning? Why a universe fit for the observer's asking? The outside view is not a harmless idealization. It assumes away the very thing under investigation, the fact that the question is being asked from within, by products of the answer. If physics needed permission to take the inside view seriously, it had been sitting in the files for 80 years. Quantum mechanics, the theory of atoms and particles assembled in the 1920s, is the one branch of physics that never had an outside view to lose. In the quantum world, observation is not a window, it is a transaction. And the meaning of that transaction was the substance of the deepest argument of the 20th century, between Albert Einstein and the Danish physicist Niels Bohr. Einstein held the classical faith, and said so in words that deserve quoting exactly. Physics is an attempt to grasp reality as it is, independently of its being observed. The world is definite, out there, complete, whether or not anyone looks. The scientist's job is to read it off, without disturbing it. Bohr answered with a sentence that still sounds like a provocation a century later. No phenomenon is a real phenomenon until it is an observed phenomenon. In quantum mechanics, a particle such as an electron is described by a wave of probability, a spread of possible positions, and the question, where is the electron, has no definite answer until an interaction forces one. The particle does not have a hidden, definite position that we merely fail to know. Before the interaction, there is no fact of the matter at all. Reality, at its base, exists in a kind of draft form, and interactions are what commit it to print. Now, a crucial clarification before we go further, because this is the point where popular accounts drive off the road. The word observation in quantum mechanics has nothing to do with consciousness. A Geiger counter observes, a stray photon observes, a grain of dust observes. Any physical interaction that correlates one system with another, that leaves a record, however humble, counts as a measurement, and the mathematics does not care whether anyone is home to read the record. When Bohr says observed phenomenon, he means registered, interacted with, committed, not seen by a mind. Keep that firmly in view tonight, because the theory we are building has been caricatured as the universe needs someone to look at it, and that is not what it says. What it says will turn out to be stranger and more careful than that. The painter René Magritte, a countryman of Lemaitre as it happens, once put the Bohr worldview on canvas without meaning to. The painting, from 1936, is called La Clairvoyance, and it shows an artist at his easel. On the table beside him sits his model, an egg. On his canvas, nearly finished, is a bird, wings spread. The painter looks at the egg and paints the bird. He is not copying what is, he is committing what could be. Bohr could have hung it in his institute as a manifesto. Observation, in the quantum world, is exactly that kind of act. It takes a spread of possibility, an egg full of futures, and delivers one actual bird. The experimental verdict for the record went to Bohr. Across a century of ever more refined tests, nature has consistently behaved as quantum mechanics says. The probabilities are real, the indefiniteness is real, and the act of interaction genuinely participates in which outcome occurs. Einstein never accepted it, and his stubbornness was fruitful. His sharpest objections became the experiments that proved him wrong. But by the time Hawking sat composing his sentence about perspective, the matter was settled physics. The quantum world does not hold still to be surveyed from nowhere. It answers questions, and the answers depend on the questions being asked from inside. Let the image settle for a moment, because it is a gentle one, and it deserves a slow breath. For 500 years, physics has been a discipline of looking outward and away, through lenses, off balconies, from imagined heights, always at the world, never at the watcher. Picture all of that apparatus now beginning, very slowly, to turn. The telescope swivels on its mount until it faces back down the stairs, at the astronomer climbing toward it. The surveyor lowers his instrument and notices, for the first time, that his own boots are standing on the terrain he has been mapping. Nothing dramatic happens. No equation changes yet. There is only the quiet, almost domestic realization that the eye was always part of the scene, that every map of the universe ever drawn has had, in its corner, an unmarked spot where the mapmaker stood. Physics turning around to include the physicist. That is the whole revolution, stated softly. Everything else tonight is the working out of its consequences. So here is where the pieces sat, on that afternoon around 2002. On one side, cosmology, a science of the whole universe, conducted for 5 centuries from an imaginary balcony outside it, now stuck at a beginning it could not describe, and a multiverse it could not tame. On the other side, quantum mechanics, a theory built entirely on the inside view, in which reality is not a finished object, but a web of possibilities committed by interaction, and which had passed every test ever devised. Hawking's leap was to see that these two facts belong together. If the universe is quantum, and it is, then the Bohr transaction does not stop at the laboratory door. It applies to everything, and that raises a question vertiginous enough that physics had spent 70 years politely not asking it. If observation participates in committing reality to print, and observations happen inside the universe, late in its history, what exactly does that mean for everything that came before us? What happens when the inside view looks backward, at the whole 13.8 billion year past? Part 8. The universe that answers when asked. The question at the end of the last chapter had, as it happens, already been drawn, decades earlier, as a doodle. The American physicist John Archibald Wheeler, the man who mentored Richard Feynman, coined the term black hole, and spent his later years asking questions his colleagues found either profound or unhinged, used to sketch a large letter U. The U stood for the universe. Its history ran up one arm from the beginning, across the bottom, and up the other arm to the present. And at the tip of that second arm, Wheeler drew an eye. The universe, his doodle said, begins in a haze, evolves for billions of years, and eventually grows something that can look, and what the eye looks at, across the gulf of time, is the universe's own beginning, including the very processes that made the eye possible. Wheeler called this the participatory universe. He suspected, long before anyone could make it precise, that observership was not a decoration on physics, but somehow woven into its foundations, and he spent his last decades asking, in various forms, one gnomic question: how does a universe of mere possibility become a universe of fact? Most physicists filed the doodle under poetry. Hawking and Hertog would spend 20 years turning it into calculation. Wheeler did more than doodle. He proposed an experiment, and the experiment has been done. In his delayed choice scenario, light from a source passes an apparatus that can be configured in two ways. One that reveals which path each photon took, one that lets the paths blend and interfere, and the crucial twist is that the choice of configuration is made after the light is already in flight. Naively, the photon must have already decided, back at the fork, whether to behave like a particle taking one path or a wave taking both. Yet when laboratories carried out the experiment, culminating in an exquisitely clean French test in 2007, the results were unambiguous. The character the light displays is fixed by the question the apparatus ultimately asks, even though the asking comes later. Nature, at the quantum level, genuinely does not commit to a past until the record demands one. Wheeler pushed the point to its limit with a cosmic version. Light from a distant quasar, bent around an intervening galaxy over billions of years, could in principle be interrogated the same way tonight, meaning the experimental question we pose this evening participates in settling a fact about light that has been traveling since before the Earth existed. The raw material for that calculation already existed, and Hawking had helped invent it. Back in 1983, he and the American physicist James Hartle had published a paper with perhaps the most audacious title in the literature, The Wave Function of the Universe. The proposal inside was scandalous in its simplicity. Quantum mechanics assigns a wave function, a catalogue of possibilities with probabilities attached, to an electron, an atom, a molecule. Why stop there? Hartle and Hawking wrote down a wave function for everything at once, the entire cosmos treated as a single quantum system. In that framework, the universe does not have one history, the way a classical object would. It has a superposition of histories, an entire ensemble of possible pasts, each carrying a quantum weight, coexisting in the same mathematical object. We will come back, later tonight, to what this paper said about the beginning itself, because that is a story of its own. For now, what matters is the ground it laid. If the universe is a quantum system, then its past is, in a precise technical sense, not a single fixed reel of film. It is a library of drafts. The move Hawking and Hertog made, formalized in a 2006 paper, written with deliberate cheek against the multiverse landscape, was to change the direction in which cosmology reads that library. The traditional method, they pointed out, is bottom-up. Assume an initial condition, some particular way the universe started, then run the laws forward and hope the result resembles the world outside your window. Every approach we have met tonight, from Lemaitre's curves to eternal inflation, reads history in that direction, from the bottom of time upward. And every one of them smuggles in the view from nowhere, because who, exactly, stands at the bottom of time, before all observers, setting initial conditions? Their alternative is top-down. Start from the top, from where we actually stand, from the concrete facts we actually observe, this universe, with 3 dimensions of space, these forces, this afterglow at 2.7 degrees, and read backward, letting what is observed now determine which of the possible histories in the quantum library are relevant at all. Do not ask, what did the beginning produce? Ask instead, given what is here, which beginnings count? The history of the universe, they argued, depends on the question being asked of it. And the question is always asked from inside, late, by us. I want to give you a feeling for the mechanism, because stated baldly it sounds like magic, and it is not. In quantum mechanics, when a possibility interacts with the world and leaves a record, the other possibilities cease to be relevant to everything downstream of that record. The draft becomes print. This is what happens, uncontroversially, in every laboratory measurement ever performed. Now apply it at cosmic scale. Every record in the present, every photon of the afterglow landing on a detector, every fossil in a cliff, every wrinkle in the sky's temperature map, acts as a constraint reaching backward through the quantum library, pruning it. Histories inconsistent with the record drop out of the accounting. Histories consistent with it remain, and among them, the overwhelmingly probable ones dominate. Observation, in this sense, does not change the past, and no signal travels backward in time. Rather, observation participates in settling which past is on the books, out of a genuine quantum plurality that was never, at the fundamental level, settled to begin with. The past is definite exactly where records make it definite, and quantum hazy everywhere the records run out. And the deepest place the records run out, of course, is the beginning. There is a children's story that captures the flavor better than any lecture, and Hertog himself reaches for it. In the Harry Potter books there is an enchanted diary whose pages are blank. It contains, in some sense, a whole person and a whole history, but it tells you nothing on its own. Only when you write a question into it does an answer surface, and the answer depends on what you asked. The quantum universe, in the top-down picture, is like that diary. It is not a finished chronicle waiting to be read. It is an archive of potential chronicles, and the questions posed to it, by measurements, by records, by observers who are themselves late chapters, are part of how any particular chronicle comes to be the one on the page. Magritte's painter looks at an egg and commits a bird to canvas. The universe, questioned from inside, commits a history. Now watch what this does to the puzzle that started everything, the question from the silent office. Because this is the payoff of the whole chapter. Ask, bottom up, why did the beginning happen to produce laws fine-tuned for life, and you are stuck choosing between a lottery with 10 to the 500 tickets and a designer? Ask top-down, and the question transforms, given that this branch of the quantum library contains observers, contains carbon, contains records being kept, which histories, which effective laws, are consistent with that. The fine-tuning stops being a miracle to explain and becomes a condition that was, in the quantum accounting, selected for, the way asking the diary about a childhood surfaces a childhood. The universe looks tailored to the question, because the question is part of how the tailoring happened. Not designed, not lucky, conditioned. I will not pretend this is easy to hold in the mind, and there is one caution worth repeating before we move on. None of this involves consciousness reaching back and sculpting atoms. The records do the work, and records are physical, mindless things, photons, isotopes, wrinkles in the sky. But even with the cautions in place, something has genuinely loosened. The past, which we have always pictured as a single iron reel, has become something subtler, A settled foreground, resting on an unsettled depth, print fading into draft as you look further back. And that raises the question this whole night has been circling, the one the top-down machinery finally equips us to ask properly. If the past grows hazier, less settled, less classical, the deeper we push toward the beginning, then what do we actually find at the bottom of the library? What is left of space, of law, of time itself, in the drafts that were never committed? It is time to run the film backward one last time, with quantum eyes open, and watch what happens to the clock. Part 9, where time melts. Come with me then, one last time, backward. Do not brace yourself. Nothing here will be sudden. You are drifting in the present, 13.8 billion years in, and the film begins to run in reverse, slowly, like a tide going out. The galaxies drift closer together, their light shifting from red toward blue. Stars dim and unravel into the clouds that made them. The cosmic cliffs disperse like breath on glass. The sky, which has been black your whole life, begins to warm. 900 million years in reverse, the first stars go out one by one, politely, like houses at the end of an evening, and a long darkness follows, and then the darkness itself begins to glow. The whole sky turns the color of embers, then of amber, then of a furnace. You have reached the wall of fog, 380,000 years from the start, where the afterglow was born, and you pass through it, into brilliance. Matter comes apart gracefully now. Atoms surrender their electrons. Nuclei split into protons and neutrons. Protons and neutrons dissolve into quarks. The universe is a shrinking ocean of light and particles, hotter every second. And as it heats, something elegant happens. The forces begin to merge. At 10,000 trillion degrees, reached about a trillionth of a second from the beginning, electromagnetism and the weak nuclear force fuse into a single electro-weak force, a union so well understood that our particle colliders have recreated its threshold on Earth. Deeper still, theory expects the strong force to join. Then, at the last, gravity itself. The universe simplifies as it condenses, shedding structure, shedding distinction, 4 forces becoming 3, becoming 2, approaching 1. And then, in the final unmeasured sliver, something happens that is not like the mergers, not like anything. The clock in your hand begins to soften. The ticks lose their spacing, then their order. Duration starts to feel like direction, like a length rather than a flow. Ahead of you, where the first moment should be, there is no wall, no bang, no door. The road does not end. The road stops being a road, the way a path fades into a beach, and the question, how much farther, quietly loses its meaning. What you just felt, in the last few seconds of that descent, is the content of the most remarkable proposal of Hawking's first career. And now we can meet it properly. In 1983, in that same wave function of the universe paper, Hartle and Hawking asked what quantum mechanics does to the singularity, the point where Einstein's equation files for bankruptcy. Their answer is called the no-boundary proposal, and it says this: as you approach the beginning, quantum effects transform the character of time itself. Time, near the origin, begins to behave like a dimension of space. Not disappears, at first, but tilts, gradually trading its time-like nature for a space-like one, so that the 4-dimensional fabric, instead of tapering to a sharp, infinite point, rounds off smoothly, the way the surface of the Earth rounds off at the South Pole. The universe, in their picture, has no boundary in the past. There is no edge where time starts, no first tick, no jagged singularity, just a smooth, closed, rounded bottom, like the hull of a ship, like the bottom of an egg. Hawking had a way of putting this that became his signature line, and it is worth savouring, because it retires one of the oldest questions in human history. Asking what came before the Big Bang, he said, is like asking what lies south of the South Pole. Stand at the pole. Every direction you can face is north. The question, which way is south, is not forbidden there. It is simply empty. The geometry offers nothing for the word to refer to. It is not that the answer is unknown. It is that the surface of the earth, being round, provides no such place, and no explorer, however determined, will ever be the first to reach it. In the no-boundary universe, before is a direction like that. Trace history backward, and you do not hit a wall with a mysterious far side. The time-like direction itself gently gives out, curls into space, and the question of what preceded the universe becomes a question about a place the geometry does not contain. Notice, too, what the rounding buys philosophically, because Hawking prized this above everything. Every cosmology before it had needed two separate ingredients: laws and an initial condition, some statement of how things were set up at the start for the laws to act on. And the initial condition always dangled, unexplained, outside the laws, a free choice made by nobody, the deepest hiding place of the view from nowhere. The no-boundary proposal collapses the two ingredients into one. If the past rounds off smoothly, there is no initial edge, and if there is no edge, there is nothing to specify. The requirement that the universe close gracefully, with no boundary, is itself the initial condition, written in the same geometric language as the laws. Hawking loved to compress it into a single koan. The boundary condition of the universe is that it has no boundary. For the first time, a cosmology needed no input from outside itself, because there was no outside, and no ledge at the beginning for an input to be handed across. The phrase Hawking used for the mathematics of this rounding was imaginary time, and I want to diffuse that phrase carefully, because it sounds like a confession of fantasy, and it is not. Imaginary here is a technical term borrowed from mathematics, where imaginary numbers are a perfectly rigorous extension of ordinary numbers, used daily in the engineering of the device you are listening on. Time measured in imaginary numbers behaves, in the equations, exactly like a dimension of space. So when Hawking says that near the origin time becomes imaginary, he is saying something precise. The underlying description of the early universe is one in which there are, in effect, 4 dimensions of space and none of time. And in a state like that, notice everything that quietly evaporates. Causality is gone, because cause and effect need before and after. Change is gone, because change is difference across time. Beginning is gone, because a beginning is a first moment, and there are no moments. What remains is not an event and a condition, timeless, changeless, the rounded bottom of everything. Lemaitre, with no mathematics for it, had felt his way to the same shape 70 years early. A primeval state, he wrote, a little before the beginning of space and time, out of which space and time would emerge. And in the 1920s, the sculptor Constantin Brancusi, knowing nothing of any of this, polished a single ovoid of marble into a piece he called The Beginning of the World, a featureless egg, without face or seam or direction, the state about which nothing can be said, resting on its plinth like a full stop placed before the first word of a sentence. I want to pause here, because if you have followed this far, something enormous has just shifted, and it deserves to be felt rather than rushed past. Your entire life is built from time, the way a house is built from brick. Every heartbeat is a tick. Every memory is an address in time. Every plan, every regret, every piece of music, every sentence, including this one, exists as a shape drawn in duration. And what the physics is now telling us is that this medium, this thing more intimate to you than space, more constant than gravity, is not part of the universe's permanent furniture. It is a local condition. It is something the universe has here, and did not have at its root, the way the earth has weather and the moon does not. The word always, which feels like the firmest word you know, turns out to describe only a province. There was a phase of reality to which the concept of when simply does not apply, and everything you have ever experienced, all of it, the whole address book of your existence, is written inside the region where time happens to hold. You are not standing on bedrock, you are standing on ice that formed, and the no-boundary proposal is the physics of the freezing. And yet, for all its beauty, the 1983 proposal could not, by itself, finish the job. Treated in the traditional way, from the outside, as one more law dictating initial conditions from nowhere, the no-boundary wave function kept embarrassing its authors. Computed bottom-up, it tended to favor the emptiest universes, ones with the least inflation, the least matter, the least structure, cosmologies nothing like the flickering fireball we actually descend from. And patched into the eternal inflation picture, it dissolved into the same unpredictive multiverse foam as everything else. Through the 2000s, this was the state of the collaboration in the office with the screensaver. The right egg, the wrong perch. The rounded beginning needed the inside view, the top-down reading, the diary that answers questions, and it needed one thing more, a mathematical language in which time could be genuinely emergent, rather than merely tilted, a language in which the question, what is time made of, has an actual answer. That language existed. It had been discovered, of all places, in the study of black holes, and it goes by the name of holography. The final piece of the origin of time is a hologram, and it is waiting for us in the next chapter. Part 10. The hologram. At the beginning. The idea that saved the theory was born from an accounting problem. In the 1970s, physicists studying black holes, Hawking foremost among them, discovered that a black hole carries entropy, a measure of hidden information, and that the amount is proportional, not to the hole's volume, as every intuition insists it should be, but to the area of its surface. Let that misfit sink in. Everything we know about information says it should scale with how much room you have. Twice the warehouse, twice the filing cabinets. Black holes disobey. All the information that ever fell in is accounted for by the two-dimensional skin of the horizon, as if the interior were not, in the fundamental ledger, a separate storage site at all. In the early 1990s, Gerard Hooft and Leonard Susskind took the hint at full strength and proposed something outrageous. Perhaps this is not a quirk of black holes, but a property of reality. Perhaps any region of space, with all its gravity and depth and three-dimensional richness, is completely described by information living on its boundary, in one fewer dimension. They called it the holographic principle, after the holograms on banknotes, where a flat film, tilted in the light, carries a full three-dimensional image. The film is not a picture of the scene. The film is the scene, encoded. The depth you see is generated from a surface that has none. For a few years, the principle hovered between insight and slogan, and then, in 1997, a young Argentine physicist named Juan Maldacena made it exact. He exhibited a mathematical universe, a curved space-time with gravity, strings, black holes, the works, and proved it was, in a precise sense, the same theory as a quantum system without gravity, living on that universe's boundary, in one fewer dimension. Two descriptions, one reality. Everything happening in the gravitational interior, every orbit and collision and collapse, has a complete translation into the boundary language, and vice versa. The discovery landed with the force of revelation. Maldacena's paper became the most cited in the history of high-energy physics, drawing tens of thousands of citations, and holography moved from the margins to the center of theoretical physics, where it has remained for over 2 decades. One caution belongs in the record, and Hawking and Hertog knew it better than anyone. Maldacena's exact dictionary works for a universe whose vacuum energy is negative, a sort of cosmic box, whereas our universe's is positive, an open, accelerating expanse. Extending holography to a universe like ours was, and remains, frontier work, and that is precisely the frontier the final theory staked its claim on. This, by the way, is the machinery behind the posthumous paper we met earlier, the one that took aim at the multiverse. When Hawking and Hertog rewrote the inflating early universe in holographic language, trading the interior picture with its runaway foam of bubbles for the boundary description, the pathological infinity simply was not there. The eternal in eternal inflation, they argued, was an artifact of trusting a classical clock, a smooth background time, in an era when time was too poorly resolved to support one. Read holographically, the ensemble of possible cosmic histories comes out finite and well-behaved. The multiverse did not need to be defeated. It needed to be translated, and in translation, it shrank. Here is the shift in plain terms. In a hologram, the third dimension, depth, is not fundamental. It is emergent, reconstructed from patterns of information on a surface with only two. Nothing in the film is deep. Depth is what the encoded correlations look like when read. Now transfer the lesson, as Hawking and Hertog did, with one audacious substitution. For the universe's history, take the emergent dimension to be not a direction of space, but time. Hawking, remember, thought in disks. So build his final diagram with me, slowly. It is the last picture the collaboration drew, the one that had been waiting at the end of the visual language he invented when his hands gave out. Draw a circle. The circle's rim is the present, the universe as observed today, from inside. The galaxies, the afterglow, the records, us. The center of the disk is the beginning, and the radial direction, rim to center, is time, running backward as you move inward. Every ring of the disk is an epoch. Just inside the rim, the era of stars. Further in, the wall of fog at 380,000 years. Further still, the fireball, the merging forces, the first trillionth of a second. In the old cosmology, this disk would be a mere illustration, a map of a history that exists independently, with time as one of its load-bearing beams. In the holographic cosmology, the disk is the reality, and the claim is this: all of it, the whole interior, every ring, every epoch, and the radial direction itself, is a holographic projection, generated from quantum information, living on the rim. Time is not the canvas the universe is painted on. Time is the depth in the image, emergent, reconstructed, real, in exactly the way the depth in a hologram is real, and not one bit more fundamental than that. And since gravity, after Einstein, is nothing but the geometry of time and space, gravity is emergent too, dissolving alongside the dimension it curves. Now walk into the picture, because this is where the origin of time stops being an abstraction and becomes something you can almost touch. There is a place in California where you can stand before the cut face of a giant sequoia, a tree that lived for well over 2,000 years, and read it like a book. The rings run outward from the core, one per year, and the tree wrote its history in them. A fat ring for a generous wet year, a tight cluster of thin rings for a decade of drought, a black scar sealed under later growth for the summer a fire passed through. Historians have matched rings in such trees to dated events, droughts in one century, eruptions in another. Douglas fir ring patterns anchored whole chronologies. Stand close, and let your eye travel inward, backward. Here, near the bark, the year you were born. Deeper, rings laid down, while empires rose somewhere far away, and the tree recorded only rain. Deeper still, the rings crowd and narrow, the young tree's years packed tight. And then, at the center, the record does something quietly profound. It does not hit a wall. There is no innermost ring with a sharp edge saying, "Here the tree began." The rings simply become finer and fainter and closer, until your eye can no longer separate them, until ring and wood and core blur into a small, dense, undifferentiated heart, where the very idea of a countable year gives out. The first year of that tree is not missing. It is unresolved. The calendar does not stop. It dissolves. That, according to the final theory, is the shape of the distant past. Walking inward through the universe's disk is, in holographic terms, zooming out of the image, coarsening it, reading it at lower and lower resolution. The further back you push, the fewer bits of boundary information remain to hold the picture sharp. Near the rim, history is crisp. Abundant records, definite facts, time ticking cleanly. Deeper in, the encoded information thins. Epochs compress, like the tree's young rings, and the reconstruction softens. And at the center, you do not reach a first moment. You run out of bits. The projection has nothing left to project with. Duration, sequence, before and after. All of it fades below resolution, and the radial direction, time itself, gives out, not at a wall, but into a blur. This is a limit of a new and absolute kind. It is not that our instruments fail there, the way telescopes fail at the wall of fog. It is not even that our equations fail there, the way Einstein's fail at the singularity. It is that the universe's own description fails there, in the same way there is no fact about the sequoia's undifferentiated heart. Hawking's old phrase, "time becomes imaginary," had finally acquired its true meaning, sharper than he could have known in 1983. Time is an emergent dimension, and at the origin it does not begin. It evaporates, and causality, gravity, and law evaporate with it. There is a last image from the collaboration that belongs here. The first time Hawking asked Hertog to draw the theory, all he wanted on the blackboard was a single circle. Hertog assumed it was the start of something elaborate, and waited, and by the end of the afternoon, the picture was still just the circle, one closed curve, the whole history of the universe in imaginary time, with us on the rim and the beginning at the middle. It became the icon of everything they did together. The man who could not hold chalk, steering a hand that could, one word a minute, drawing the universe as a disk, whose depth is time, and whose center is the place where depth runs out. But the circle was still hiding one secret, the deepest of them all. We have watched time evaporate at the center. We have not yet asked what happens, in that same blur, to the laws. Because something else runs out at the core of the disk, and when you see what it is, you will understand at last why a book about the origin of time is named after Darwin. Part 11. Laws that grew like trees. Every story we have told tonight has quietly assumed that one thing, at least, was waiting at the bottom of the universe, the rulebook. Time might bend, space might stretch, matter might dissolve into light, but the laws, surely the laws were there from the start, presiding. Even the no-boundary proposal, even the hologram, seemed to leave the rulebook enthroned. The mathematics that describes how time emerges is still mathematics, and it is natural to assume it was in charge all along. The final move of Hawking's final theory is to deny exactly this. In the blur at the center of the disk, where time loses resolution, the laws lose resolution too. Not just our knowledge of them, the laws themselves. Below a certain depth, there is no fact about how many dimensions space has, no fact about which particles exist, no fact about the strength of any force. For the same reason, there is no fact about the sequoia's first year. The information that would constitute such a fact is not there. The rulebook is not waiting at the bottom of the universe. The bottom of the universe is where the rulebook runs out. If the laws were not there at the start, then they arrived. And the physics of their arrival is something we can actually say a great deal about, because its later chapters have been measured. As the young universe expanded and cooled, it passed through a series of transformations physicists call phase transitions, each one a freezing. You know this process from water. Above 0 degrees, a glass of water is the same in every direction, perfectly symmetric. Freeze it, and the crystal that forms picks particular axes, particular alignments, structure the liquid never had. Nothing chose the orientation of the crystal. Chance did, and then the choice hardened. The infant universe froze in the same way, repeatedly. As the temperature fell through 10,000 trillion degrees, the unified electroweak force crystallized into two forces, electromagnetism and the weak force, and the masses of the fundamental particles snapped into their values, set by how the freezing happened to break. Earlier freezings, at higher temperatures, are thought to have fixed the strong force, the menu of particles, perhaps the number of usable dimensions of space itself. Each transition is a fork, where the mathematics permitted several outcomes, and the universe, cooling too fast for deliberation, committed to one. What we call the laws of physics, in this picture, are the frozen record of those commitments, not the eternal architecture of reality, but its earliest habits, hardened. Now add the ingredient that makes this evolution rather than mere unfolding. At each fork, what supplied the alternatives was quantum randomness, the same irreducible chance that decides when an atom decays. And what settled which alternatives matter, across the whole ensemble of possible histories, is the top-down conditioning we built 2 chapters ago. Of all the ways the freezings could have gone, the histories that count from the inside are the ones consistent with the records that exist, with a universe that contains structure, chemistry, observers, questions, variation, supplied by quantum chance, selection, enforced by conditioning on what is actually here. Say those 2 words together, variation and selection, and you are speaking the language of Charles Darwin. This is why the book is called what it is called. Hawking and Hertog came to believe that the origin of the laws of physics is a Darwinian process, a genealogy of frozen accidents, winnowed retrospectively, in which the regularities we call laws emerge the way species emerge, contingent, historical, and unplanned. The barcode we met at the beginning of tonight, the birth certificate supposedly printed before delivery, turns out to be something else entirely. It is a fossil record. The universe was not issued its laws. It grew them, and the growing shows. There is a pair of drawings that puts the whole idea into 2 images, and Hertog delights in setting them side by side. The first is one of the most famous pages in the history of science, a notebook sketch from 1837, made by Darwin shortly after the beagle brought him home. It shows a spindly, branching tree, drawn fast, with a few words above it, I think. It is the first known drawing of the tree of life, the moment the idea of common descent, of species as a branching genealogy rather than a fixed catalogue, escaped onto paper. The second drawing is Lemaitre's, from his notebook, almost exactly a century later, 1936. A hand-drawn curve of his hesitating universe, the one cosmos in his zoo, with room for stars and readers, rising, pausing, rising again. 2 sketches, 100 years apart, by a naturalist and a priest. For 90 years, science treated them as belonging to different worlds. Darwin's tree describing the contingent, evolved, accidental living world. Lemaitre's curve describing the lawful, mathematical, eternal physical one. Biology was history. Physics was legislation. The final theory's deepest claim is that this division was never real. The 2 sketches show the same kind of thing, lineages. One draws the descent of species, the other, read with the final theory's eyes, draws the descent of a universe, laws and all, one branch of a genealogy of frozen choices. Physics and biology, Hertog argues, are 2 stories of a single evolutionary building, and each story has a ground floor. Run biology back, and you reach the origin of life, where the laws of biology dissolve into chemistry. Run physics back, and you reach the origin of time, where the laws of physics dissolve into the timeless blur. Neither rulebook precedes its world. Every rulebook, everywhere, is a residue. And watch what this does, at last, to the mystery that summoned Hertog through that office door. The universe's unreasonable hospitality, the fine-tuned barcode, the carbon resonance, the 6 numbers. The question, why were the laws set so perfectly for life, assumed the laws were set, that the tuning happened first, and life threaded the needle after. But if the laws crystallized through a sequence of chance-frozen forks, read top-down from a branch that contains observers, then the fit between laws and life is not a miracle at the front of the story. It is a consistency condition across the whole of it. The universe fits life the way a riverbed fits its river. Stand on the bank and marvel. Every curve of the channel matches every curve of the water, to the millimeter, along its whole length. What are the odds? But the bed was not machined in advance to receive this river. Water and rock shaped each other, over ages, until fitting was simply what they did. No designer carved the channel. No infinity of rivers was needed to explain the one that runs. History did it, mutual, patient, and blind. In the final theory, our biophilic barcode is a riverbed. The tuning is real, and it explains nothing, because it is not an input, it is an outcome. Hawking held this idea to the standard he had carved above his own door. The mission statement he wrote for his Cosmology Centre in Cambridge is blunt. It exists to develop theories of the universe that are mathematically consistent and observationally testable. Fine words, and a hard question follows them. A theory about an era with no time, no law, and, by construction, no surviving light. What could testable possibly mean? Hertog answers with an honest comparison. Their situation, he says, is like Darwin's in the middle of the 19th century, in possession of a mechanism, variation and selection that made sense of everything visible, but with a fossil record too thin to force the case, and no way to watch the process run. What rescued Darwin was that the fossils existed, in the ground, waiting for better tools and more patience. The final theory's wager is that its fossils exist too, and we already know their substance, because we met it at the wall of fog, gravitational waves, the one messenger that escapes the universe's opaque first act. We know the medium is real. In September 2015, the LIGO detectors caught space itself ringing from 2 black holes that collided over 1 billion light-years away, radiating, in a fraction of a second, more power than all the stars in the observable universe emit together. The fossils of creation would be subtler, a background of primordial gravitational waves generated as time itself crystallized, and, printed on the microwave sky, a faint curling pattern in the afterglow's polarization, the fireball's light combed by those first ripples. The hunt for that pattern has already had one famous false dawn, in 2014, when a South Pole telescope's claimed detection turned out to be galactic dust. The search continues, chastened and sharpened, and in the 2030s, a trio of European spacecraft flying a triangle 2.5 million kilometers on a side will listen for the low hum directly. Somewhere in that data, if the theory is right, is the birth certificate of time, the real one this time, written not in law, but in ripples. We have every piece on the table now. A beginning that is not an edge, but a fade. A dimension that condenses like frost. Laws that grew like tree rings around an unresolvable core. And a night's worth of promises coming due, because there is nothing left to prepare. It is time to answer the question we began with. Part 12. The True Origin of Time. Let us gather the whole night into a few slow sentences, and then say the thing plainly. We began with a universe unreasonably fit for life, governed by laws nobody could explain, traced back to a beginning no equation survived. We watched the one formula answer shatter into a landscape, and the multiverse answer dissolve into predictions that could not be made. We watched Hawking turn physics around to face its own observers, watched the quantum library of histories open, watched time tilt into space at the rounded bottom of the world, and watched the hologram thin, ring by ring, toward a core where the bits run out. And we watched the laws themselves revealed as frozen history, a riverbed carved by its own river. Every piece is on the table. Here is what they spell. Time is not fundamental, and it did not switch on at the Big Bang. There was no first tick, no moment of ignition, no cosmic starter's pistol. Time is an emergent dimension, a depth reconstructed from quantum information, and toward the origin, it does not begin. It condenses, gradually, the way frost condenses on a window, the way a note fades in from silence, so gradually that no line can be drawn where it starts. Follow it backward, and duration softens into geometry, sequence into blur, until the very distinction between time and space, between happening and simply being, dissolves into a timeless quantum state about which the phrase, "what happened," cannot even be framed. The true origin of time is not an event. It is a dissolution, crossed in reverse. The Big Bang is real as the afterglow in every cubic centimeter of the room you are lying in, but it is not the origin of time. It is the crystallization of time, the era in which the dimension you live along hardened out of something that had no dimensions to offer. And this answer can only be read from where you are reading it, from inside, downstream, in the one place answers exist, because the inside is all there is. Hawking's old joke has been waiting all night for its final form, so let us give it. What came before the Big Bang, he said, is like what lies south of the South Pole. But walk the answer one step further now, with everything we know. At the actual South Pole, there is at least a pole, a marked point, a brass line for tourists to straddle. The origin of time has no pole. Approach the distant past, and the meridians of before and after do not converge on a point. They fade, like a map dissolving at its edge into unmarked parchment, until the question of direction quietly stops applying. The oldest question our species knows, what came before, is not answered by the final theory. It is retired. Honorably, the way which way is south retires at the pole, and something gentler is uncovered beneath it. Not a wall at the beginning of the world, but a horizon, beyond which lies not mystery, but no beyond at all. Honesty requires the next sentence, and the theory's authors would insist on it. This is a hypothesis. It is mathematically serious, physically motivated, and, its makers believed, testable in principle. But it has not been confirmed, and its subject is the least accessible era in all of reality. The path to confirmation runs through the fossils we named, a background of primordial gravitational waves, and the curling imprint they would press into the polarization of the afterglow, patterns that would carry, in their shape, information about how the dimension of time condensed, how fast, how smoothly, through what sequence of freezings. If those patterns are found, in the polarization maps, or in the millihertz hum, a laser triangle in space will listen for, in the 2030s, cosmology will do, for the origin of time, what the pigeon-haunted antenna in New Jersey did for the origin of matter. Until then, the theory stands where Darwin stood in 1859, mechanism in hand, waiting on the ground to give up its record. Physics has been wrong before, beautifully. It may be wrong here. But notice what can no longer be unthought, whatever the verdict. Time has been moved, permanently, from the list of things assumed to the list of things to be explained. That shelf never gives anything back. And now, the story keeps the last of its promises, the one about the man. In 1988, in the closing lines of the most famous science book of the century, Stephen Hawking wrote that a complete theory of everything would be the ultimate triumph of human reason, for then we would know the mind of God. That is the Einstein inheritance, fully flowered, one final formula, read from nowhere, closing the case of existence. The man who spent his last 20 years in the office with the scrolling screensaver came to believe that no such formula exists. Not because we are too weak to find it, but because the universe is not the kind of thing that has one. Its deepest regularities are grown, not decreed, and every reading is taken from inside. Late in his life, Hawking said it in words that deserve to be heard slowly. "I used to believe in that final theory," he admitted, "but now I am glad that our search for understanding will never come to an end, that we will always have the challenge of new discovery. Without it, we would stagnate." Hear what that sentence costs, and what it buys. The man is renouncing the trophy he had promised the world, the summit his entire early career pointed toward, and he is calling the loss a gift. His collaborator says the final words Hawking composed for him, assembled through the sensor on his glasses at a word a minute, touched this same point: the unended search, the universe with the human inside it. Perhaps the genius was never the theorems. Perhaps it was this, a mind that could change, completely, at the end, and never once look back. Stephen Hawking died on March 14, 2018, at 76, 55 years into a 2-year prognosis. His ashes were interred that June in Westminster Abbey, in the nave, between the graves of Isaac Newton and Charles Darwin. And you can read the placement now, like a sentence in stone. Newton on one side, eternal law, the barcode, the universe as legislation. Darwin on the other, descent, contingency, the tree, the universe as history. And between them, the man whose final theory says the two were never rivals. That law is what history hardens into, that mathematics and evolution are one process, seen at two depths. On the stone itself is carved the formula for the temperature of a black hole, his signature discovery, the equation that first taught physics that even the darkest objects in existence slowly give themselves back. In 1958, the philosopher Hannah Arendt warned that modern science, watching the world from an imagined outside, was building a picture of reality with no room for the human beings inside it, and that such a picture must end by estranging us from our own condition. 60 years later, a man who could move one muscle in one cheek answered her from the far side of physics. The deepest theory we have of the beginning of everything now requires the inside view, carries the observer in its foundations, and cannot even be written without acknowledging that someone, somewhere downstream, is asking. So let it come to rest, here, in the dark, with you. The dimension you are drifting along as you fall asleep tonight. The one that carries you from this sentence to the next, from this evening into tomorrow, is not the silent absolute it pretends to be. It condensed, in the universe's first unresolvable blur, out of a state with no yesterday in it, and every when that has ever existed, every date, every childhood, every night, like this one, is written inside the region where that condensation holds. You have spent your whole life inside a dimension with an origin, a thing that grew, the way the sequoia's rings grew around a core where counting fails. And if the final theory is right, then your asking, tonight, is not outside the story. The records and questions of observers are threads in how the universe's history holds itself together at all. Somewhere in the oldest light in the sky, combed into its faint polarization, the proof may already be waiting, the fossil of the moment the clock began to set. A satellite not yet launched may find it while you are still young enough to hear the news. Until then, we are left with the priest's poem, which turned out, 90 years early, to be the physics itself. In the beginning, there was the now which has no yesterday, because yesterday there was no time for one, and out of that timeless quiet, slowly, the first duration thickened, and the rings began. That is the true origin of time, not a bang, a beginning without an edge, still unfinished, still crystallizing, carrying you gently forward inside it, toward morning.